At the heart of physics lies a powerful equation that helps us understand motion, energy, and the underlying principles of nature. The Euler-Lagrange equation is not just a mathematical tool, it is the key to unlocking the natural laws that govern everything from the motion of planets to the behavior of particles and systems in motion. In this video, we will dive into the world of the Euler-Lagrange equation and explain some of the most important fundamental concepts, how nature finds the most efficient paths, and how these principles shape everything around us. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to understanding what is Euler-Lagrange equation. So we start basically first with this very question that what is Euler-Lagrange equation? First, I would like to show a simple definition, what it is all about. Then definitely we are going to go into the mathematical understanding. So the definition tells that the Euler-Lagrange equation is a very fundamental equation. It is used in the calculus of variations and it is used to find the path, curve, surface or function that minimizes or maximizes something which is a certain quantity. Now what this quantity, what it minimizes and maximizes, we will come to that part later. So if we can take this kind of a shape, it can be any kind of a curve. So you can see here, this is where it actually minimizes and this is where it maximizes. And these things can be anything, time, energy or distance. So from here what I can tell you is that if you're trying to minimize or maximize these things, time, energy or distance, that depends on the shape of the curve, which you can see right now on the screen. The shape of the curve or behavior of the function, the Euler-Lagrange equation gives the rule of the function which must satisfy to achieve this. So there are various formats of Euler-Lagrange equation, but I would like to show you this or this. More or less both of them actually means the same, only it is a matter of notation, usage, bringing the left hand side to the right hand side, putting a minus sign, all those things. So this is actually an Euler-Lagrange equation which is very much specialized to classical mechanics, and this is the general form of the Euler-Lagrange equation which is used in the calculus of variations. So here is a quick summary that you can think this equation, which seems to be a little bit complicated, is a set of instruction for finding the optimal or the best shape of the curve. So we can also say that the Euler-Lagrange equation is a kind of a rule. It gives the rule that the function must satisfy in order to achieve this. Now it can be the curve, it can be calculating time, energy or distance, or it can be various other things. So from here what we can understand that definitely Euler-Lagrange equation, like the Lagrangian, it is a tool in order to achieve certain calculations, certain measurements, certain calculation of paths. And if we plug in those values x and q dot and y prime, we will get our job done. So this is basically a mathematical beautiful tool where you can plug in those values and you can get it. Now the question that comes to all of our mind is that if I take this format, which is very used in classical mechanics and it is easy to understand, is that why do we see so much of partial differential equations? So why do we at all need this? And why we need to study all those complex partial differentials? So obviously any mathematical tool, for example the Lagrangian or the Euler-Lagrange equation, definitely should have an objective. It just not come out of the blue that we have to calculate the partials and need to study. So as there is a famous saying that necessity is the mother of invention, but what exactly does that mean in the context of mathematics and physics? What was the necessity? Now in the world of classical mechanics, the Euler-Lagrange equation actually emerged from a pressing need in order to address a problem. And this is known as the Tautochrone problem. And there is a wonderful history, a very motivating story, which I'm going to tell you. And this Tautochrone problem, in order to solve this Tautochrone problem, we got perhaps one of the most beautiful equation of physics and mathematics. Now Johann Bernoulli, you all know a Swiss mathematician, first posed this challenge in 1696. Now, what was the problem? It is called the Tautochrone problem. Now, you can see in the animation that there are certain beads which are following. First, let us understand that what is the etymological meaning of this word Tautochrone. So here first you see that these are the beads which are sliding down. So the question first is that what is the curve along the bead sliding frictionless under the influence of gravity, which will take the same amount of time to reach the lowest point regardless of the starting position of the curve. So it can start right on the top, at the middle, at the end, it doesn't matter. But what is the curve? What would be the shape along which the bead will slide? Or we can say it also in this word, that if ball slides without friction down a curved ramp, as you can see these balls are sliding down, what shape should be the ramp? So that the ball always takes the same amount of time to reach the bottom no matter where it starts. This is actually the problem that was posed. So as I was telling, the etymological meaning, tauto, which comes from the Greek word same or equal, and chrone means time. So tautochrone actually means the same time, and it is perfectly matching with the problem. So the problem is telling that wherever the bead is starting on the ramp, what shape should be so that the ball takes the same amount of time. So same and time, taut and chron, is the tautochrone problem. Now, this is a simpler understanding, that the problem is to find a curve that ensures the ball takes exactly the same time to reach no matter where it starts. Now, this problem was actually solved by the Italian mathematician, physicist and astronomer Joseph Louis Lagrange. I am not going to tell much about his biography, but you can go ahead and read it. In 1766, on the recommendation of Leonhard Euler and D'Alembert, Lagrange succeeded Euler as the director of mathematics at the Prussian Academy of Sciences in Berlin, Prussia, where he stayed over 20 years and produced many volumes of work and winning several prizes of the French Academy of Sciences. Now, as Joseph Louis Lagrange solved the problem which was posed by Johann Bernoulli, history tells that he was around 19 years old. He was just 19 years when he solved this problem, and is sent to another great mathematical giant, that is Leonhard Euler, the Swiss mathematician. And here comes the most interesting story. I'm quoting these lines from the book Tales of Mathematician and Physicists, written by Simon Gindkin. I hope I'm pronouncing his name correctly. And what Leonhard Euler replied to Lagrange on the 10th of October 1759 is this: the importance of the question motivated me to the point where, with the help of your illumination, I deduced the analytic solution myself. However, I decided to conceal this until you publish your results, since in no way do I want to take away from you any of the glory that you deserve. Astounding, a remarkable example of scientific ethics. So the letter suggests that although Euler has developed the tautochrone problem analytically, however, he won't publish it until and unless Lagrange is given a chance, because he is younger to him, and it should be brought in front of the world. So he writes that in no way I want to take away your credit, because you deserve the credit, you deserve the glory. And this was a great example of Leonhard Euler's leadership and bringing forward young scientists. So from this we got what is called the Euler-Lagrange equation, and the entire Lagrangian mechanics emerged. Now, I am not going to show you a mathematical deduction of the tautochrone problem, but the basic idea is that until and unless you understand how elegant and beautiful the Euler-Lagrange equation is, you won't understand without dealing and understanding the tautochrone problem. So first, let us understand that what was the challenge. So the challenge was basically to identify the exact shape of the curve that satisfies this condition, and proving mathematically that the curve works for any starting point. That means what? This problem could not be solved with simple geometry as processed analytically by Leonhard Euler. It required new tools to analyze motion and forces in a much more abstract way. So here comes the role of the Euler-Lagrange equation. Now I am not going to deduce that, but what we can understand from this is that to solve the problem mathematically, one important part is this t. Now t is expressed as a functional, not a function. It is a functional in terms of the curve y of x, and the functional represents the total time taken by the bead to slide from the starting point, for example x1 y1, to the lowest point on the curve. On the numerator, what we see, this one is basically, this accounts for the curve's length element. That means the distance traveled along the curve. And this denominator part gives the speed of the bead. That means it is actually derived from the conservation of energy. So how did the Euler-Lagrange equation solve it? So the Euler-Lagrange is a powerful mathematical tool from the calculus of variations, and the quantity to optimize is basically the time taken to the ball to slide down the curve. It used what is called the principle of least action, and thirdly, the most important question which comes is that why it is complex. I'm going to say we could have solved with Newton's laws of motion or analytically. The complexity is because this time, the time t, is as decent as functional. That means the time t depends on the entire curve, not just specific values of x and y. So that was basically the problem. So when we talk of the complexity, we should understand the basic root of this problem. The challenge is that a functional should consider the entire shape of a curve. It is not that you get any xy point or a single point. So here is an example which I would like to tell you, that as because the functional considers the entire shape of the curve, this is why finding the problem was difficult. Instead of just solving f of x equal to 0, it has to be solved with the whole function y of x that satisfies the minimization condition, which is the functional of t. So we should remember one thing, that a function gives a relation between two variables, f of x equal to x square, whereas a functional maps functions to numbers. So how the Euler-Lagrange equation actually solved it? I mean to say, what was the solution? So the solution which came up is finally what is called a cycloid. So the solution to the Tautochrone problem is a specific curve which is called a cycloid, and a cycloid is basically a curve traced by a point on the rim of a rolling wheel, which looks something, a kind of an animation I've tried to show you, something like this. Now this shape has actually got a unique property, and this property balances the travel time regardless of starting height, because the geometry perfectly compensates for differences in speed and distance. So if we solve the solution, the differential equation of cycloid, we get this one, x equal to r theta minus sine theta, and so on. So it was proven that the cycloid is the only curve, or you can say that this is the shape that the curve is going to take under gravity, taken at the same to reach at the bottom. And the Euler-Lagrange equation showed that this curve perfectly balances the effects of speed, distance, and perfectly ensures that the time to slide down is constant. So theta is the parameter, r is the radius generating of the cycloid. So what are the key equations involved? First is this one, which is called the time integral. The second one is the Euler-Lagrange equation, and third, which was the solution to the curve. So the problem demonstrated actually the power of calculus of variations and led to a deeper understanding in physics, particularly in motion, energy, and system optimization. So this is actually what is the Tautochrone problem, the basic root, the reason why the Euler-Lagrange equation was developed, and it shows the great personality of Leonhard Euler, giving Lagrange a chance to come forward and show the world his talent. So now we come to what we call understanding the equation. So we will break down the Euler-Lagrange equation step by step, and we will see what it comprises of, and then we will consider the components. So I'm considering this one, which is a little bit easier part to understand. So first we take this one, d by dt. This is what is called the total time derivative of the generalized momentum. Wait, I'm coming to what I mean by generalized momentum. It measures how the momentum changes with time as system evolves. So I've written time rate of change of momentum. Then this 2 curly L is simply the Lagrangian, that is kinetic energy minus potential energy, denoted as T minus V. Then this entire partial of Lagrangian upon partial of Q dot, this can be taken as what is called a generalized momentum. Now if you are wondering what is in a generalized momentum, I will come to that part later. This Q dot is actually representing what is called a generalized, it is a generalized velocity. And this part, partial of Lagrangian by partial of Q, this is called the generalized force. It's actually physically represents the generalized force which is acting on the system. And what is this Q? One Q dot is the generalized velocity, which is the time derivative of Q, and this Q is nothing but the generalized coordinate. So again, to repeat that, first, this Q on the right hand side is a generalized coordinate, which is a variable used to describe the configuration of the system. The Q dot you can think as something like dq by dt. It is the time derivative of Q, representing velocity associated with the generalized coordinate. The curly L is the Lagrangian. Partial L by partial Q is the generalized force, and partial L by partial Q dot is the generalized momentum. Obviously Q dot, because it is a derivative, so it measures the generalized velocity term. So overall, what we can say is that the Euler-Lagrange equation describes how a system evolves by stating that the rate of change of the generalized momentum, which is on the left hand side, is equal to the generalized force acting of the system. Overall, we can say it is a balance of the laws of nature. So here is another version of this. This part is the generalized momentum. This part is the generalized force, and the time rate of change of the generalized momentum equals to the generalized force. But we will look also later that this actually leads to F equals to ma. This is Newton's laws of force. It is Newton's second law. So what we can say that F equals to ma, remember that it is a generalized form of the Euler-Lagrange equation is a generalized form of F equals to ma, and F equals to ma actually only applies to linear system, but the Euler-Lagrange equation is generalized coordinates and with constraints and lot of flexibilities. So if you go by the deduction, you will see that it is ultimately resulting into Newton's second law. But Newton's second law is applicable only to linear system. This extends and goes much bigger, much broader, and it encompasses a lot of problem in physics and mathematics. So here we get three important concepts that we are going to learn now. First is, what is a generalized coordinate? Why do we need that? Second is that what is generalized velocity, also how it becomes effective. And third is what is called generalized momentum and why it is required and what difference it carries from the momentum and how effective it is in our in mathematical physics. So first we will start with what is called the generalized coordinates. So the generalized coordinate, I am just showing the Lagrange equation so that you know which element. So this is this Q. So generalized coordinates are basically used in order to make a system much more convenient. Configuration of a mechanical system becomes much more convenient. So we use the term generalized because we want to distinguish that it is not the general or the usual coordinate system of a Cartesian system. So that is why we are generalizing, that is, we are making it much broader. So I will take this first example of a single pendulum, the oscillating single pendulum, and the simple pendulum constrained to move in a plane which is described by the angle theta. The pendulum makes the vertical. So instead of xy coordinates, the first in a simple pendulum, we are considering this theta. Now we come a little bit complex, which is a double pendulum. That means a pendulum attached to another pendulum and can be described by two forces, or two angles I should say, theta 1, angle of the first pendulum from the vertical, and theta 2, that is angle of the second pendulum to the first. And here theta 1 and theta 2 are basically the generalized coordinate. There is another example also, I have not gone into the mathematical part, which is the bead on a wire, which you have already seen. So here you can see that the generalized coordinates intrinsically accounts for the system constraints. They are not restricted to specific type of coordinates like Cartesian system, etc., and can represent any variable that fully describe the system's configuration, which can include angles, distance, or any kind of abstract parameters. So this is a simple example. Single pendulum, double pendulum, bead on a wire, etc. are examples of generalized coordinates where we are extending beyond the Cartesian coordinate in a nice and elegant manner. Now, as you can see that if I consider a cube, for example, and here is this one, a nice particle, the yellow one, you can consider it as ball or something. So here the number of generalized coordinates equals the number of degrees of freedom of the system. So how many degrees of freedom it has got? Obviously 3. A particle in a 3D space has got 3 degrees of freedom. A simple pendulum, which we have showed already, has 1 degree of freedom, which is the angle theta, and the double pendulum has got 2 degrees of freedom, that is theta 1 and theta 2. So from here, how do we generalize? Now let us assume that if we have a system and this system has got n generalized coordinates, so we are moving from 1, 2, 3 to n. So for n generalized coordinates, q1, q2, q3, q4, ... it goes up to qn. The system of the state is fully determined, which is by the generalized coordinates qi. So we take the time derivatives dqi by dt, which are generalized velocities, and here qi denotes distance and t denotes the time. So now if we take this generalized system traveling from q1, q2 up to qn, then what will be the Euler-Lagrange equation look? Simple like this: d by dt, the total time derivative, divided by partial of L by partial of q dot, and where I will actually denote 1, 2, 3, 4, and it will go ... up to n. So this is the use, the essence, the strength of using generalized generalized coordinates, so that we are extending beyond the normal coordinates from 1 to 2 to 3, and up we can go up to n. And the Euler-Lagrange equation surprisingly fits so well by defining these partial derivatives and taking the time derivative. So this is actually the striking work this is the genius of Euler-Lagrange. So now what we can tell that this is the mathematical tool which I was telling. So you just need to plug in the values. What is t, what is qi, and you get a complete evolution of the system in any n degrees of freedom. And this was not possible with Newton's laws of motion, which was restricted only to linear systems. Now let us understand that why this generalized coordinates become so advantageous. First is this one: by choosing coordinates adapted to the system, you often reduce the complexity of the equations, obviously. The second thing which comes is the constraints. Constraint means fixed lengths, surfaces. They are actually naturally incorporated in the choice of coordinates. You don't have to do anything else. And the third part is that it works with any Cartesian systems. Any coordinate system, Cartesian, polar, cylindrical, spherical, or any system. So we can say that generalized coordinates are a flexible and a powerful way to describe the configuration of the system tailored to a specific problem. So you have a problem, you have the coordinates, you can just plug in the values in the Euler-Lagrange equation, you get the complete dynamics of the system. So we are done with the generalized coordinates, and now we move into what is called the generalized velocity. And we will start with the general mechanical velocity. I mean to say the typical velocity that we know as dy, dx by dt. So in this equation, where does the generalized velocity comes? Q dot. So if I take a kind of a Cartesian coordinate, traditional velocity is straightforward. So we say v sub x equals to dx by dt, and v sub y is equal to dy by dt. Simple. So in generalized coordinate, velocity corresponds to what we call the time derivative of the generalized coordinates. Velocity obviously has to be a derivative. So it is a derivative of what? Not the usual Cartesian coordinate, but the generalized coordinate, which we have just seen in the video. And remember, this generalized coordinates may or may not represent a physical distance. I will come to that part later. So if I take a kind of a equation like this, here you can see it automatically inherits the corresponding generalized coordinate. What is that? Qi, which we have just seen in the Euler-Lagrange equation few seconds earlier. So if I would say that qi equals to dqi by dt, it inherits. So if qi is a distance, for example, if it is in meters, then qi dot is a velocity, example, meters per second. And if qi is an angle, for example, in radians, then qi dot is an angular velocity, that is radians per second. So you get a hand-in-hand matching with that. Now if I come to polar coordinates, what it would be simple, r dot would be equal to dr by dt, which is a radial velocity. You can say rate of change of radial distance, and theta dot would be angular velocity, that is the rate of the change of the angle, which is not a linear distance. So this is basically the concept of what we call generalized velocity. Now generalized velocity, as because it is a derivative, it inherits the corresponding generalized coordinate and it is a derivative. So what we have seen earlier, here also it will apply for the same. So a partial of q dot is the derivative, is the time derivative of q, and partial of q is basically representing the generalized velocity coordinate. So same here, if a system described by n is described by q1, q2, qn, then the time derivatives are generalized velocities. So here the Euler-Lagrange equation becomes this one, which we have seen earlier, and the term is used because we want to differentiate with the Cartesian coordinates as defined in the system, and instead they correspond the rate of change of any generalized coordinate that uniquely describes the system. Earlier it was meant by any generalized coordinate system which is from the Cartesian. Here it is generalized velocity, which is again a time derivative of the generalized coordinate. Very simple and clear. Now if you want to understand, if you might ask me a question that what is the physical meaning of what we call generalized velocity, then I would say just understand that it is the rate of change of the generalized coordinate with respect to time, nothing more than that. And as you can see, for a particle in a Cartesian coordinates, if I say x, y and z, say for example let us say x and y, then the traditional velocity would be vx equal to vx dot and vy equal to vy dot. And for a simple pendulum which is oscillating, the generalized velocity theta dot is the angular velocity. So the kinetic energy of a system would be defined by this as a function of the generalized velocity. So T will be equals to kinetic energy, the Lagrangian, q1, q2 dot 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 up to qn would be what, q1 dot comma q2 dot, and it will go up to qn dot. So this can be written in this form definitely, and the generalized velocity appears in the Lagrangian, and its derivative is something which is very, very central to the Euler-Lagrange equation. So from here what we can say, we can summarize that the generalized velocity enables the use of Lagrangian, and you really don't need to calculate the force explicitly. It can done in terms of energy. The same as the Lagrangian. You don't need to force to express a system. You can just use kinetic and potential energy. It works for any coordinate system, and it naturally incorporates the effect of constraints into the equations of motion. So qi dot is the time derivative of the generalized velocity, and qi represents how qi changes with time, and this is the Euler-Lagrange equation, where this part is the crucial for deriving the equations of motion, and this one is involves the dependence of the Lagrangian on the generalized velocity. Now I would like to show you that when we are saying that it is a generalized velocity, so it has have some kind of a mathematical interpretation. So I am taking the same cube and I am taking the same particle. So I want to define that if you are taking this in a Cartesian coordinates, we can easily relate generalized momentum to this definition. So we are taking the x, y and the z coordinates. For a particle, say for example mass m, which I have not written, moving in a 3D space, the generalized coordinates would be this: q1 equals to x, q2 equal to y and q3 equal to z. The velocity would be given by this: q1 dot equal to x dot simple, which are just the components of the traditional velocity. And the Lagrangian is this one: L equals to T minus V. Kinetic energy is half mv squared. So we have taken 1/2 m multiplied by x squared plus y squared, x squared dot plus y squared dot plus z dot squared, and minus potential energy. Potential energy is what? Just the x, y and z. So the generalized, this is the kinetic and this is the potential energy part. So the kinetic energy of the x coordinate would be this one. And obviously what you can deduce from here is that this mx dot is nothing but a representation of the classical momentum P equals to mv. And in a similar way, you can do the further calculations to get py and you can get pz. So this is how the generalized velocity, in some way it comes down. It helps to attain various other coordinates. It becomes easier, and how it comes to the classical momentum part. Already, although we have not dealt with generalized momentum, so now we look into the last part of our video, that what is generalized momentum. So generalized momentum again is a generalization of the momentum. So where does it feature? This part. So this is the generalized momentum. So first let us go by the general definition. So what is the general definition? The general definition says that the generalized momentum Pi, remember it is generalized, not only a linear, it contains all the momentum, is defined as the partial derivative of the Lagrangian L with respect to the generalized velocity, obviously Qi dot, where Qi represents the ith generalized coordinate. It can be 1, 2 or up to n. So here this is actually the definition. So generalized momentum is a generalization of the classical Newtonian momentum P equals to mv. And if I see this equation, you can see q dot I. This is basically is what? Simple, the time derivatives of the generalized coordinates qi. And the Lagrangian can be written as this qi dot and t, where this t represents the kinetic energy and this v represents what is called the potential energy. Now, the next part of our video answers a very crucial question, that why we are taking the partial derivatives over here. We could have taken a simple derivative, we have not taken a partial derivative, ordinary derivatives which we call. Now, I am going to answer that with an analogy. Now, in physics generally, derivatives often represents rate of change. We know that. In the context of Lagrangian mechanics, the generalized velocity, which is q dot I, represents how fast a particular generalized coordinate qi is changing with the time. So you can take this as a central concept, which one is highlighted, this one in green, that the idea is that the generalized momentum pi associated with the coordinate, generalized coordinate qi, is actually related to the kinetic energy of the system and how the kinetic energy of the system changes as the velocity q dot I changes. So what happens is that if we take this part, if we take the partial derivative of the Lagrangian, which actually includes the kinetic energy with respect to q dot I, what we are doing is that we are essentially isolating, we are deducting, we are subtracting the contribution of the specific velocity component to the overall momentum of the system. As generally we do the partial derivative, keeping one constant, varying the other, keeping the second constant, varying the third, and so on. Let me give you a very quick analogy, pictorial analogy, it would be easier for you to understand. Think it in this way. Say for example, there is an x and y coordinate. This car is moving along the x coordinate. This car is moving along the y coordinate. And imagine you have a car moving in these two dimensions, both in x and y. So the total kinetic energy depends on both the x velocity and the y velocity, obviously. Now, if you want to know how the kinetic energy changes specifically, so this is the total kinetic energy, right? Which includes both the x and the y part. Now, if you want to know how the kinetic energy changes specifically due to the x velocity, you need to take the partial derivative of the kinetic energy with respect to the x velocity, which looks like this. And this actually gives you the momentum component associated with the x direction. So that is the reason we are doing the partial derivative, so that we can reduce this part and we get the x, then the y and the z, and it can go up to n. So taking the partial derivative of the kinetic energy t with respect to the x component velocity vx gives the x component of the momentum, that is p sub x. And here how it works. I mean to say, very simple. What we do is that we take the partial derivative of t with respect to v sub x, which gives this equation. Since only v2x depends on v sub x, we get this one. The result is this one, and this results to the momentum p, which is defined as p equals to mv. Here it is p sub x equals to mv sub x. So this actually shows you that how do we get back to the classical momentum part. So what we can say is that taking the partial derivatives of the Lagrangian with respect to the generalized velocity is a kind of a mathematical technique to extract the relevant information about the momentum associated with the particular degree of freedom, which we have dealt in the generalized coordinate. So this process is something which is very fundamental to understand the dynamics of a system within the framework of the Lagrangian mechanics. So this is what is called the generalized momentum. Now it is the time to make a quick summary of what we have learned. So we will look once more into the equation, and we know that this is the time rate of change of generalized momentum. We now know what is the generalized momentum. This part is the generalized force. We also know what is a generalized force. We know what is a generalized force. We know what is generalized coordinate. We know what is a generalized momentum. And from here we can find out a nice definition that it balances the two, ensuring that the system follows the path that is the integral of the Lagrangian. So the Euler-Lagrange equation actually solves a lot of problems in mathematical physics. First, in physics, it helps you to find the path of least action, obviously, Lagrangian mechanics. You have seen in my earlier video. It obviously unifies principle because it provides a universal framework to solve optimization problems, yes. And it leads to Lagrangian mechanics. That means it forms the basis of modern theoretical physics going up to quantum field theory, etc. And it ultimately solves a lot of complex problems and make our mathematical physicists and scientists and mathematicians and physicists' lives easier, because the complicated problems involve too much of differential equations which can be solved mathematically. So that's it. We will take a pause in today's video, and I would like to thank you very much for watching this video. If you like this video, do not forget to subscribe by clicking on the subscribe on my channel Physics for Students, and also click on the bell icon so that you get all the updates and notifications from Physics for Students for any videos and announcement. Let us remember that the universe is full of lot of beautiful wonders, and we are here to explore together. You can contact me at this email ID, and you can personally follow me in my LinkedIn, Twitter and Instagram account. Physics for Students would be soon back with lot of surprising and fun-loving videos on physics, mathematics and other areas. But till then, may the good Lord be with you.